Okay, welcome to the stream today. Today we will be continuing our work to design an HDL parameterizable image processing. So you can choose the window size and it will generate the window size. It's really fun because it has nested for loops inside a VHDL process. This allows you to actually process any size of kernel you want. So we've done the coefficient multiplication, and we've done that. So what we need to do next, it's actually going to be outside this loop, right here. We need to do a sum tree, and I think we're going to do kind of like this n log n type, or this n log function to help us determine how this tree is going to work. So for a 9, so if we have a 3x3 window, right, and it's going to be 9 units total, we're going to go 16 down to 8 down to 4 down to 2 down to 1 to create our parameterizable sum tree. And if we have a 5x5, it's going to be 25. So then we want to do a 32 to 16, and then repeat down to 1. And then a popular one is a 10x10 filter, right? I don't think we'll be able to do that because of the lack of resources on here. But we want to do a 10x10 filter. Then we have 128 down to 64 down to 32 type of summation tree. So let's figure out how to do this. Since we're doing a 5x5 filter already, let's go ahead and just kind of hard code the for loop that would do this and look at how we're going to parameterize it. So window com8 is our output. So what we're going to do right there, yeah, we're going to do a quick for loop. Just I'm going to do another one of these just to help me keep it going. So now we need to create a new type, right? We had all these types here, like T window 16. Want to do the summation. We want to keep it 16. So what we want to do here, so let's copy this line, right? We're going to call it T sum type. And we want to make it to 32 in this situation. We'll figure out how to get the nlog solution to get that better lined up. So we have that. So let's go back here and how many do we need? Let's do a type T sum array is array. We want to 1, 2, 4, 8, 16, 32. So 6 to 2 to 5 of sums. We just need a T sum of T sum. Okay, so then we're going to do a signal of sum tree. I'm going to call it T sum array. And yeah, we want to assign it all to zeros. Okay. Now so what we're going to do first here is we're going to default this sum tree. So we're going to do sum tree 0 is going to default to just kind of that level of zeros. And then we're just going to do sum tree of I is going to equal that. So, okay. Now let's generate another loop. So it's gonna be 4 to 15. Yep, and we're gonna end loop. First off, actually, I want to see what type of, did we do standard logic vector? I want to do signed. Let's do signed here, right? And we want to just go ahead and cast these as signed values as we convert to our okay, that way we can add them easier without all the configuration. So here we're going to want to do, we're going to say 1. And what we're going to do is we're going to do I times 2. So we're going to do sum tree of 0 of I times 2, right? Plus sum tree I times 2 plus 1. And this should do our sum tree just very nicely. But we also have to, we want to do this thing right here where we are going to zero out anything else so that we know what is zeroed out. Because there's going to be, these things are going to be, and when it's zeroed out, the synthesis should hopefully ignore those. So let's go ahead and do this for the next one. 2. And this time we're just doing I to 7. And 2, 1, 1. Oh, and save it to 3. So we're going to do 3, do I to 3, 4. No, that was supposed to be 2. There. 2, 3, 2, 2. Okay. Now let's do this one more time. 4. 4, 3. We have one more to do. And that should be a 1, actually 0 to 1. Oh. Not inclusive on that one? Because these are array size minus 1, right? 0 to array size. Oh, no, that's right. So we're good there. And then we're just going to kind of do a simple tree, which is just going to be 0 to 0, like not doing anything. And here we go. So I think then we could parameterize this in a way that we do an n log n type of functionality. Then we should be able to get this parameterizable to fit different kernel sizes. Okay. Let's go to simulation, and we have our thing here, which is working. It'll be interesting as it adds all of those. But this is all good. So let us regenerate this. Yeah, so the plan is for the streams as we go along this current chapter. We're gonna finish this up, and then we're gonna compare it to HLS resource-wise, and I guess maybe performance-wise. It's going to be fun getting the HLS performance-wise to work. Set that to waveform. Want to radix that to signed values. And let me get, I'm going to stick you guys. Back up and rolling. Okay, here we go. We have this right here, and we're just going to enter that into the tickle console. See what happens. Okay. Go to this. Send that. Index 33 out of bounds of 32. Oh. Why kernel array size? What happened? So we have 0 to 31. Kernel array size. Oh, why is this 5? Yeah. That was doing a 10 by 10. We'll try that later. Okay, let's redo this. Rebuilt. So, you guys, does anyone have any other suggestions for summation tree? Unless I pull out my arithmetic book and look at being able to carry the sum into multiple additions without doing the sum tree into the end. I mean, I could look at doing that. I probably need to catch up on my arithmetic sometime, so I might be good to look at doing the arithmetic for this. Okay, so let's see how this sum tree worked. Okay. Unsigned decimal. Okay. So now we want it signed decimal. Sorry, radix signed decimal. 5, -4, -2, 45, 6, 43. Zero. Yeah, look at our sum tree. It worked. Worked great. So let's parameterize that. Let's let me go. There's a GitHub. We go to my softcore project. We can get something useful. So let's go to my softcore project. I think I used that in the no, not the softcore project. We're in the warp core project. Go back, the warp core. do projects. UART test source. HDL, the UART transmitter. So there's this function. Where is it? Not in here. No. I think it might be. Let's see if it's passed down the transmitter core. Right here. Log to C. So let us copy this and put this into our type package. So we have a function in our type package. Okay, apparently this needs to go. Where did it get in here? It was inside the architecture, apparently. Boom. Okay, so this is here, then we need to define the sum tree internally. So we probably need to take this, stick that there, and take this and put that there. So because what we want to do is we want to use this log2 function, and we're going to create a natural, write that like that. Copy. And what's this going to be? Some depth. Some depth. And it's going to be kernel array size. So this should give us 6. So we should be able to do some depth minus 1. And then we want to do 2, some depth minus some depth. Okay. Well, let's see if the sizes are what we expect and the operation works the same. Go ahead and copy this guy again. Oh, launch simulation failed. So we go here, scroll up, index our range for target sum tree, 79. 79. Index 5, line 153. Ooh. Log 2 of 25, 4.6. We round up in this thing? So I guess, yeah. And what is 2 to the 5th? 2 to the 5th is 32. Okay, so we're good there. So let's try this again. Okay, so it's happy. Everything looks good actually. So let's try to parameterize it. So all of these should be good. kernel array size. And so we want to do a for loop from here. Okay, so we want to do a for loop of I of j in 0 to some. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we'll do 1 to some depth. Loop. End loop. Okay. So let's see what we can do here. So we want to say j. We're going to zero out j, and this has to be something about j, right? So this has to be 2 times j of do some depth, right? So divided by that. And minus 1. So, okay, we have 32, right? Some depth is 33. 32 divided by 2 is 16. And this will be j minus 1, j minus 1. All the way to 5, which should be, this should be equivalent to each other, right? 2, oh, 2 times 4, 2 times this, so this has to be that. Down to 0 to 0. Okay, so I think that's the way to do it. So let's go ahead and delete these. Kind of scary just doing that. Wow, I've never seen this type of stuff in VHDL code before. What you do to try to parameterize and we'll try 3, and then we'll try is it working? And if we, nope, copy, paste. $128. Cool. So let us parameterize this for a 3x3 kernel, right? 3x3 kernel. So there's only going to be 9 values. Let's rerun this, and while we're doing this, we're going to want to comment out these 9 values, yeah. Okay. See. Now we go here. See how there's different stages? Index 8 is out of bounds. 0 to 7. Oh, 3 is exactly. No, wait. So we have a 0 to 7. Be a 0 to 16. Oh. +1. because we did a -1 in the other thing. How about we just do this? You know, we just do just to make it make more sense. Kernel size times kernel size. Put that there. Redo it. That should move it up to the 16. Four. Let's copy this. We'll see. We'll be. Let's get these back to our radix of sign decimal. Okay. Added correctly, added correctly, added correctly. 21, 24, 45, 27. Okay, good. Now adds these two, adds these two, adds those two, 27, adds these two, 37, adds those two, 24, adds those 64. Parameterizable thing. Okay, so we've proved this. Now let's do an extreme, right? Let's 10 by 10, right? 10 by 10. Our parameter kernel filter. So yeah, let's relaunch simulation. Okay. 0 to 27, look at that. Let's run the same thing. And we look here, it just brings them down. Form radix, sign decimal. Boom, boom, boom. Okay, now here's what we're gonna do. We're gonna do a let's convert it back to 5, do synthesis, and look at the utilization. Wow, that worked. I was expecting this to be more complicated, harder, or something like that, but not too bad. We're gonna rerun this and see what we get by slices. So, okay, so originally we had around 17,500. Let's see how much this adder tree increases the complexity. Go ahead, 1750 is our original thing. Our 17,500. Close design. I guess we can go to log, trace watch the synthesis finish. Already finished. Okay, let's open the synthesized design and do a report utilization. Let's see what we got. Report utilization. So 17,500. That's interesting. I mean, we're timesing it by 3, 4,000. I mean, that might have been the 10x one. Yeah, let's go ahead and do the 10x. That's probably the one we were looking at. We're gonna times this by 3. We're still like you're using them. This is just for one channel. If we try to do a 3-channel one, we're probably looking at a 30% utilization. We're gonna just do one channel and then create an HLS that's 5, a 5 by 5, and do one channel of that, and compare the two utilization between HLS and this really nicely knit HDL design. Okay, so so yeah, let's quickly change this back to a 10 because that's I think what the last one was done. Rerun synthesis. Look at the utilization on that. Run synthesis. Yeah. Yeah, do it. And then I think we'll be done for the day. And that should be it. Tomorrow we'll add the barrel shifter, which will be a fun thing to do. Lower limit, upper limit. And then we should be good for there. Then the next is just providing the parameters. Yeah. It's interesting. Blunixa. How is your name actually spelled? Blue Nexels. Blue Nexels. That I create a video filtering. So let's see how big this file is. So this allows you to do a 3x3 kernel, 5x5 kernel, 10x10 kernel, a 20x20 kernel, up to 100x100 kernel. So we could easily do video filtering of any needs using this filter. There's a little bit like we won't be able to do. I don't think we can do an erosion or a dilation. Just the way it works, because the way an erosion works, it says if any of them are 0, blank the whole thing, and if a dilation is if any of them are 1, if anything is 1 in the 1 is above your threshold in the filter, make that a value. I don't know how I can do. Is there an erosion kernel definition? Yeah, so one thing we can do here is an erosion or dilation. So we would have to create a different filter for erosion or dilation. But here we can already do a ton of video image filtering. And stuff that, I mean, we just basically made a convolution, right? No, convolution acts a little bit different. You get more values at the end. But we have our coefficients. Oh, we did a matrix multiplication. Why can't I don't. What would you call this? I can't remember what you would call this. But we made it parameterizable. Pretty cool. Okay. Oh, it's still 15,500. So I guess those the sum tree didn't add that much, or it's just not. Oh, we didn't add it to the output. Yeah, let's add it to the output real quick. Oh, that's rough. Okay, we need to add this to the output. How are we going to do that? Is it T window T? Okay, what we're going to do is we're going to have to do another for loop here. For loop. Oh, we'll just do this, right? End loop. And we're going to just, I guess, register the output. And it's going to be output of I is, what do we need here? We need to state can be sum of some depth, right? I, and we want to make it a standard logic vector. Okay, rerun synthesis. Look at that. So okay, so just send this to someone. Okay, so let's look at synthesis. Yes, there's a lot of zeros, propagating zeros. We see that a ton in the there's things that will always be zero and never assigned. A little scary. That'd be about a 1/8, 1/7. Yeah, yeah. So morphology is really interesting. The idea of erosion and dilation. And so erosion is you look at a window. If anything in the window is zero, that means you're going to zero out that pixel that that window is centered on. That's erosion. And so you basically can erode. You basically erode everything that is not or so many pixels wide, top and bottom. And dilation is the opposite. If there's even one pixel that is on within that region, you're going to highlight that one. So that will dramatically increase the image. And we did this a lot. We did this when we did the baseball catcher. We did erosion and dilation to try to filter out any noise in the screen or in our image. Remove noise and only care about the data that was concrete. Okay, so we increased about 3,000 slices. We still haven't done optimization, so this be interesting how this works. Okay, you used lots of blurring, yeah. So for our final project in the baseball catcher, we actually implemented our software thing into an FPGA. So I converted all the software things we were doing in OpenCV to HLS kernels, and I ran it on a Zynga UltraScale Plus device. And it required a 14 by 14 kernel, which was pretty interesting in this design. I wish I had this little operator thing. So this would be super easy to do. We can do edge detection, stuff like that. And yeah. Okay, so that's it. We added 3,000 more LUTs. It'll be interesting to see this when it's cleaned up. So Wednesday, be on Wednesday. Wednesday we're going to do a barrel shifter, upper limit, lower limit, and then the operator is done. Then we have to do line buffers, and then we have to create the AXI light interface that will configure all these parameters that we can make this parameterizable. And we'll see how it goes. Thank you for watching. I will post this to YouTube later, and have a great night. Bye.